Greetings everyone, my name is Dishant Parekh and I'm here to present the paper titled S-Extension Patch, a simple and efficient way to extend an object detection model. The paper introduces a new technique called the S-Extension Patch, or also known as the Similarity-Based Extension Patch, which deals with the problem of adding additional classes to an existing object detection model. There are currently many approaches available to deal with the said problem, but these approaches have one or more of the following three limitations. First, the data availability. The overall availability of the data for training a new class can be quite low in some of the approaches. For example, in joint training, where it is required to create a master dataset with the old classes as well as the new classes data and then annotating them to build the model. Now, the developers may not have these old data available for retraining the existing model with additional classes. Second, the pre-processing time. This is seen not only in joint training, but also in fine-tuning as well as the learning without forgetting technique, because all of them require more or less some annotations. For example, in learning without forgetting, we'll need the annotations of the new classes as well as in the fine-tuning technique. But in joint training, it would also require to annotate some of the old data as well as the new data. So it creates a huge workload for training the model. Finally, the training time of particular model training. When we talk about the object detection model with additional classes, we have to train the object detection model entirely, again, in some way or the other. In learning without forgetting, it can be just adding a layer and over the architecture and training that. In fine tuning, it could be just training it from the last epoch, and in joint training, it has to be done from the scratch. But all of these training times are quite high compared to some of the problems we have at hand. Hence, the solution comes in the form of leveraging similarity. When we talk about the similarity-based extension, there are two main things. First, the definition of similarity, and second, why similarity or how it could help us. The entire concept of extension patch works on leveraging highly similar classes to train upon. The similarity is calculated between the base classes and extension classes. Base classes are the classes which are there in the existing model, and extension classes are basically the additional capabilities that we want to train it on. If the extension class is highly similar to any one of those base classes, then the technique would drop down the training time to up to 10% of the original on the same computational resources. Let's take an example. If there is a base class named car and there's an extension class of van, both of them are highly similar. Now what will happen at the time of inference? If we show a picture of van, the model is going to confuse it as car, and that's why we don't have to change the entire detection model, but only the label of it. And for that, a simple classifier could also work. But the problem is in identifying those compatible classes and to then train the classifier on it. Hence, here's the approach of the entire S extension patch. First, as explained, finding the compatible classes. The second is to build the classifier, and third, to configure the inference such that it can maintain the same inference as the original model. As you can already see, the technique is going to use a dual model system for inference. And so, to maintain the inference timing, we use a special technique called dual parallel inference technique. Now let us look at each of these steps in detail. First, the compatibility search, meaning finding those base classes which can help leverage the similarity with one or more extension classes. The most important part of this step is the calculation of similarity, what to use and how to use. The similarity calculation is based on a simple cosine-based distance calculation, but distance is not calculated directly on all the images, but is generated over the feature centroids of each class, also known as the class representatives. The reason for this is that we do not need to compare each image in every single class inside the dataset. It will just create an additional computational toll as well as increase the error in similarity. And that's why we just take all the images and create one feature representative of each class and then compare the distances between them. The next slide will make the entire flow clear. So, as seen here, we take all the images inside the extension classes as well as the base classes. For example, if there are 120 images for the classes, we'll have all of those images in every single class. And then we pass a feature extraction step over it. This is achieved by running the images through a ResNet 152 model and extracting the vector after the average pooling layer. This gives us a feature vector of length 2048. Next, all the features in a particular class are fitted in a KNN model or any of the unsupervised clustering model, and the cluster center is set as a feature centroid or representative for that particular class. After this, the similarity matrix is created. by the pairwise distance computations between the feature centroids of each class in the base as well as the extension classes. The compatible classes are selected based on the similarity threshold set, and here we are using 0.05 because we saw that it works pretty well. It can also be changed depending on the problem at hand. Now that we have the classes to be trained upon, let's train the classifier. Training the classifier is quite straightforward. Take all the images from each of the compatible classes and create a master dataset to fit a classifier on. Now on to the inference. This is one of the most important steps as we have to defend the inference timings on this new technique. As discussed earlier, the technique uses two models, and to maintain this inference timing, we use a dual parallel inference technique. The first question that arises in anyone's mind is that if there are two models, is the image going to be processed twice? Well, the answer is no. The image is only going to be processed by the detector, and then the classifier would use the entire feature vector which is already extracted through the detector. Second, if there are going to be two models, then how the inference timing is exactly going to be maintained? Well, the answer lies in the name, parallel computation. We use a threaded approach with a shared memory. Here is a flowchart for the same. Here, we take the video, and from that we can extract each frame, and that frame is going to be passed to the detector. Once the prediction is there, we basically put it in a shared memory and update it with the frame as well as the prediction of it. Next, the classifier would create a lock on this particular shared memory and update the label if at all it is required. This all is done while the detector is processing the second frame. And this way, the entire process happens in the time of detection model, as the classifier takes lesser time to update than the detector model takes to prediction. The result could be compared in 5 categories, as defined by the authors of the original learning without forgetting technique. First, the need for preprocessing, basically annotations. As our technique only requires to train a classifier, it has no need for any such preprocessings. All the 3 techniques, learning without forgetting, fine-tuning, as well as joint training, have low, medium, and high need for data preprocessing, respectively. Second, the speed of adaptation. Learning without forgetting is a great approach, but it is a difficult system to adapt and code upon, and hence this is one of the most significant aspects of the extension patch, as it is easy and can be appended to any system, be it one-step detection model or two-step detection model. Time for training is another such factor. All 3 of the previous approaches require training an object detection model in some way or the other. As the extension patch only requires to train a classifier, the time for training is the least. Finally, the performance of the old and the new tasks. Performance on the old task remains the same, as we do not touch the object detection model whatsoever. The performance on the new task is high because the classifier would have lower classes as well as a new model to check the results, making the overall approach less erroneous. Hence, with the use of extension patch, we can get the task done in just 10% of the original time. This makes it possible for developers to quickly replace the system till the original model is trained with all the labels. Extension patch not only offers faster training, but also speed and ease of adaptation, as it can be appended to any existing system, given it fulfills the similarity threshold condition. Here, I'd like to add that although the extension patch covers most of the limitations, it is a relatively new technique with a lot of scope still to be explored. The technique can be further improved by using other similarity measures or appending the path directly to the model while training and keeping a unified architecture. The extension patch can be made more scalable by using a two-step detection model and using the patch for just the classification step and fine-tuning the model there. It can significantly improve the speed and the time to implement the inference strategy. The strategy is also being experimented on different visual models, including the classifiers and graphic rendering algorithms. Similarity-based extension patch is easy to adapt to any system, can be trained quickly and maintained, and even in some cases increases the accuracy as well as the inference speed. Thank you so much for your attention, and I now yield my time to the panel for any questions.